Hello, my name is Carlos Manuel Cruz Segundo. In this occupation, I will present you the work titled Impact of Electrospinning on the Structural and Functional Properties of Chitosan-Based Membranes for Water Remediation. Nowadays, water pollution is one of the most serious environmental issues globally due to its harmful consequences on the ecosystem and public health. In particular, chitosan based products have found applications as effective biosorbents due to low cost and high contents of amino and hydroxyl functional groups, which shows significant absorption potential for the removal of various aquatic pollutants. Due to the above, the present research aims to investigate the impact of two distinct fabrication methodologies: electrospinning to obtain a nanostructured membrane and casting to obtain a membrane, on the structural integrity and functional performance of chitosan-based membranes. The methodology followed for the fulfillment of the objective is as follows. Initially, the chitosan was hydrolyzed with sodium hydroxide for 48 hours. Then the solution was centrifuged at 4,000 rpm for 15 minutes. The precipitate formed by hydrolyzed chitosan was neutralized and dried at 60 C. After that, a solution of chitosan hydrolyzed polyvinyl alcohol was prepared using acetic acid as solvent. With the resulting solution, the chitosan nanostructured membrane was obtained by electrospinning and the chitosan membrane by casting technique, to finally analyze by means of Fourier transform infrared spectroscopy, X-ray diffraction, and scanning electron microscopy, and thus analyze the results. Figure 1 shows the FTTR spectra of the polymers used for the formation of the membranes, which shows that the chitosan after hydrolysis still shows the absorption bands corresponding to the hydroxyl and amine groups, which is an indication that despite the breaking of bonds by hydrolysis, it still retains the characteristic structure of the polysaccharide. On the other hand, the FTR spectrum of PVA shows the characteristic band of the hydroxyl groups. Figure 2 shows the RDX of chitosan, hydrolyzed chitosan, and PVA. It can be observed that the hydrolyzed chitosan presents a higher crystallinity than with respect to the initial chitosan. This can be attributed to the structural rearrangement arising from the hydrolysis process, while PVA presents a diffractogram characteristic of a semicrystalline material. The FTR spectra of the nanostructured membrane and the membrane are shown in Figure 3, from which it is observed that the nanostructured membrane presents a higher intensity in the absorption bands corresponding to the hydroxyl, amine, and carbonyl groups than the membrane. This is attributed to the fact that the nanostructured membrane, due to its higher surface area, has more functional groups, while the membrane, being more rigid, decreases the presence of these groups. Figure 4 presents the diffractograms of the nanostructured membrane and the membrane, where it is more clearly seen that the membrane is more crystalline than the nanostructured membrane, which explains the behavior in the intensity of the FTR absorption bands. Finally, Figure 5 shows the surface of the membranes, where it is observed that the membrane is smooth, while the nanostructured membrane has a rough surface, which is characteristic of a crystalline and amorphous material, respectively. Figure 6 shows that nanofibers with an average diameter of 250 nanometers were indeed formed. In conclusion, these results demonstrate that electrospinning improves the functionality of chitosan membranes, expanding their potential for use in the filtration of conventional metals and dyes present in aqueous media. Thank you for your attention.